crossroad puzzle. So how to make the traffic go in parallel. Okay. Now what we are left is here is just animations for you to do the revision. So I won't talk about it. So you guys go to take a look at it. Then we will go to the next, in the last IPC classic problem. Okay, the classic problem is, we call it reiterated problem. Okay, I know the progress for the database course. Does the database course talk about two-phase locking? No. Ever heard of the locking or a serializable problem? No. Okay, good. So I'm a little bit ahead of our database course. No problem. So I guess you have I look at the examination list. Okay, 120 something people in the database. So I hope that here already have at least half of you guys will doing database. So you know that, well, database, what is a writer? Writer is those guys who call select from where, right? You are calling select from where. So if you are a database user, I think that you should understand that it should be a concurrent read-only access for users, right? I won't expect that you will be surprised that I allow you to do the concurrent access, right? So, does it mean that it is a simple mutual exclusion problem now? It seems not. If I allow multiple processes to access the same piece of data, right? It's just, well, because we're doing read-only, I start reading it and then I produce results. None of the business about the other guys. Of course, I won't order is reading because I'm also a reader. So it is not a simple mutual exclusion problem, yet if I have a writer exists, okay, so who are writers? Those who call insert values, those who call updates, those who call create tables, those who call drop tables, okay, they are writers. Basically, it's change the database. Now think about it while you are doing the change and allow some people to do the read. You can think of the consequence, okay? So in Amazon, the cloud database, not the cloud database, the cloud system, we have one property is very important to uphold. So I think no course in this university will talk about it. It's called eventually consistency. Okay? Eventually, some people write the database and some people read it. Eventually, they will have a consistent view. Okay? Now, I'm not talking about this consistent in an eventual sense. I want a consistency happen, okay, when this writer step in the system, I either make two choices. One choice is this. I don't want eventually the database will converge into a consistent view. I don't want. I want the view immediately being locked by the writer. Okay? So when I try to write it, you guys try to read it, shut up, don't go on. You have to undo all your partial work for this guys, or you don't be able to start any work. Okay? I finish updating the view, updating the table, then you guys start to read it. So then I will make a consistent view over these four guys. Because I'm the writer, I know that what I'm going to write, and the reader will read the most up-to-date versions of data. This is choice number one. Choice number two is the reverse. Okay, just like gangsters. Okay, the gangsters in Hong Kong, right? Or in blues. Okay, if you know what I'm talking about. So the blue guys are gangster. So they are occupying the database. They don't leave. Okay, so what is the meaning of they don't leave? You know, if a writer tries to step in, the writer tries to step in and want to update the thing, basically you need to block them out. Now, what if there is a reader already start reading the database? Should you kick him out or not? Now, this is the second choice. You can choose to, hey, this bunch of reader, okay, you guys have the, you guys come to the database first. So I serve you. Okay, I serve you, but how about the writer? You have to stop there, wait for some moment. Then after all reader leave, I give you the database. Now, this is the true choices. Choices, not implementation. And you know, I have to give you one of the choices. They are of different implementation. I will give you an easier implementation. This is an easier implementation. An easier implementation is biased to the reader. Let the reader go on. Okay? So later on, when you look at the solution, you will find that I always give priority to the reader. Okay? Remember, I give priority means that when a writer appears, I will stop the writer, not stop the reader. Okay? So of course, this is a hybrid versions. Okay? So hybrid version means that if a writer already can take the database, I will also block other writers. Okay? So what is this problem? This problem I said is database problem. It is a kind of mix. Okay, not a simple mutual exclusion problem. Of course, you can say that the database is a mutual exclusion resource. Once a writer step in, okay, as if I should freeze this important resource, okay, or it is a shared object. Now, if you think of it in that way, okay, later on I will tell you what is the problem of our solution. Okay, so how about the synchronization rule? Okay, what is synchronization? Synchronization means that, okay, those processes will cooperate. So what are the cooperation rules? So the cooperation number one is, while we have a reader reading, now reader is reading, not means reader just come to the database. It's already start reading the database content. So what happens? Others reader will be allowed to go on. I don't know when you come here, but when you come to the database, you can still work together with this guy. So here's your friend. Okay, your friend has opened the door for you. You just go into the door or go to the room. Now, what about writer? Because writer tried to order the table, order the database, drop the database, delete entry. I don't know what you are going to do, but yeah, you should stop because someone is reading. Okay? And how about the third rule? The third rule is the writers is actually having a higher priority. When the writer is in the database as if it's hold the database exclusively. No one can get the database. Okay? So you can see that writer seems to have more power but very restrictive. Okay? This writer is very restrictive in the sense that if I have writer, okay, I will block. I am a writer, okay, in the database already. I will block my friend. My friend is also a writer. I will also block my enemies. The enemies are reader. Okay. How about I'm a writer, but I find that there is a reader already reading, so I'm blocked out. I cannot go on. So I says this is very restrictive. Okay. So to visualize it, this database is just a mutually exclusive resource. So I will use a binary semaphore. Use a binary semaphore to, to create a condition such that it is mutually exclusive. Now, but how about if I set up in this way? Okay, if I set up in this way, now it's okay because I have only one reader and one writer. When a reader is reading, I will down the semaphore. Down the semaphore is binary, so when I down it means I lock the database, so this guy cannot go in. But if I have other readers also in the system, I will have trouble because I will also block another reader. If I treat this database semaphore as a simple mutually exclusive mechanism. Okay? Now I give you the full code. The full code is not difficult to understand, okay? Full code is here. Now look at two different pieces of code. One piece of code is easier to understand, the writer. The writer is easier, okay? So what is the writer? The writer is just have a very simple design. We have an entry. Because I'm writer, say I just pretend that I have something to work. over the database, so I have to prepare some write statement or data. Then I will try to grab the lock. Okay, in a normal database system, you cannot see this line. You cannot see this line. When you try to execute your query, basically you will execute this line. Okay, this down call, whether I can grab the access to the database. And if I can, I will try to update it. Okay, of course, the update should be successful. Then I will call up to unlock the database. So very simple, right? If I have a bunch of writers, all people are writer, okay, then you will have a sequence very simple. Lock the database, update it, unlock, and another guy, lock the database, update, and unlock. Now, how about the reader? Wow, the reader seems to be bigger. So, I give you several, I should say that 2 minutes, okay, several minutes, too much, okay? Understand this code and tell me what is the use of one semaphore, which is extra, called mutex. This is called DB, right? I said that I will pretend that the database is a shared resource, so I use a DB to access mutual exclusion access to the database. But what is this mutex? Seems to be something extra, right? Of course, I call it mutex. It's also added as a mutual exclusion access. Look at its initialization value. It's 1. It's 1. So I want it to be the binary semaphore, either 1 or 0, 1 or 0. Now give you 2 minutes. You can discuss it with your neighbor. Tell me, what is the thing that this mutex want to protect? It's not database. Database is protected by DB. Look at it. And how to discover the answer? Look for the lines of code that are being enclosed by the up-down call over mutex. Up-down call over mutex. When you down it and then up it, what are the things being encapsulated between it? Yeah, give it 2 minutes. Okay? Yeah, go ahead. You need to think about it. Okay. Usually this type of question will appear in examination. What is or are? I don't know is or are. And if you already know the answer, tell me how to set up the concurrent access condition. One more minute. Yeah, look closely the up and down call over the mutex. What are the statements between them? Okay, thumbs up. Now, in between the up and down mutex call, the red one is the entry, the green one is the exit. Now, what are they in common? They have a variable called db as well as the recount. Is it going to protect the db semaphore? Using a semaphore to very common. Is it? The thing that is yes? No? So that means it protects this variable. Recount. The thing that is yes. Yes. Some of you raise your hand. Some of you is in a quantum stage. Okay, sometimes yes, sometimes no. Okay. Yeah, unless I inspect you. Okay, so what is your answer? Protect recount. So what is the status of recount? Is it a global variable or a local variable or a shared variable? It's shared variable. So is it a semaphore? No. So it's only a simple variable. Okay. So if you find a shared simple variable, not a semaphore, so basically you need to protect it using mutex when you try to read and write it. Okay. So whenever you try to read and write it, you find a mutex protecting it. We seldom use mutex to protect another semaphore. It's not useful, right? How you need this, okay? Because it's already when you call down or up semaphore, you already disable all the interrupts, so you don't need extra protection. Now, you protect the recount, okay? So you protect the recount, plus and minus, and also the if condition. Okay? So no matter it's read, no matter it's write, I will protect them all. Okay? So why we need that recount? Now back to the physical meaning. The read count is basically to count the number of readers. That means your brothers, your sister, how many brothers and sisters in the system. Okay? So whenever you have brothers, you are the reader, your brothers comes in, okay, no matter what, it will go through the checking, and after the entry, the increment of the recount will be incremented by 1. And when you leave, okay, your brother's count will be dropped by 1. Now, so basically, it's a conditional gate. The gate to the database. It's a conditional gate. If you are the first of your kind, so that means you're a reader, you are first of your kind, then you will try to down the DB. Of course, it may fail because you may have a writer in there. Now, if there is no writer, you will be successful downing this DB. And when you will release the lock, you release the lock when I have say three reader executing. So the read count will be 3. When I have one guy sleep, 3 drop to 2, 2 drop to 1, 1 drop to 0. Then all readers will quit the system. Then you will up the DB. Okay? So this is a conditional gate. Whenever you have your brothers, your sister in the system, the DB won't be unlocked if you have your brother and sister. If no, you are the first of your kind, you have to try to down DB. Okay? You have to try to down DB. Any questions? Now let me ask you. Think very clearly what I want to say. You can see that I call down mutex, okay? And I have a danger that when I down DB, I will be blocked. Okay? Will I cause the entire system go into deadlock state? Will I? Now remember what I said. Here I already grabbed the mutex. Now I'm holding one thing and I wait for another thing. Yeah, seems to be the previous what is that? Oh, producer consumer case. I'm holding one semaphore. Now I want to have another semaphore, but another semaphore won't allow me to get it because it's already grabbed by the writer. So this guy is holding something and goes to sleep. Will I have a potential deadlock scenario that frees the entire database system? I'll give you 1 minute. Will I? Also, this type of thing will appear in a final exam. Very quickly, this question. 3 seconds. Think clearly what are the conditions for deadlock. One guy is holding one thing, waiting for another thing, but they form a cycle a resource grabbing cycle. Okay, I want this, you also want the things that I'm holding, so we're deadlock. Okay, or I forgot to tell you what is another name for deadlock. We call it deadly embrace. Deadly embrace. Embrace means this action. Okay, we have a very excellent translation in Cantonese. 攬住一齊死 ，deadly embrace。普通話我不懂怎麼翻譯，不然我放 please。Okay, 攬住一齊死 ，very nice. Will I have deadly embrace here? Who think yes? No? Who think no? Okay. Good. So, yeah, no. We won't have deadly embrace. We won't have a deadlock scenario because when this guy is holding the mutag and it wants to have DB, say the DB is being held by writer, say DB is holding by writer, do writer need mutag? No. Who need mutag? Only reader need mutag. Let's say other writers is being blocked because it cannot get the mutag. What is big deal? No big deal. Because this guy will eventually release DB. And this guy don't need mutag. We don't have deadly embrace. Okay? Just an order that, okay, after this guy finished executing, this guy will be unblocked. And it is for sure. So we don't have a resource waiting cycle. Okay? Only a linear relationship. Okay? So back to the one more properties of this solution. You can look at this solution. This solution has got many questions, right? This properties is the concurrency, right? You find there's a high concurrency here. The concurrency is about the reader. Once I have one reader and the reader won't go away, I can allow 1 million writer to be blocked here, but another 1 million reader executing concurrently. Okay, so it seems it's unfair, right? It's unfair to this guy of 1 million. Okay, I have more process. Okay, say 10 million writer, but still I have two reader reading the database. Sorry, there's 1 million. I don't care whether it's 1 billion or 1 million. You will block. Okay, only two blocking 1 million or 1 billion writer. You don't want the solution, then you have to change this code. Okay, and this code is not easy to change. Once upon a time, the first year I teach this subject. Okay, I don't know how good or bad the students are. Okay. So I set up the questions. The question is, when a writer arrives at the system, all reader coming later than that writer should be blocked. Not enjoying this high concurrency. Of course, I have a solution. Okay, but usually I won't put this question up. Okay, that question is nuclear weapon. Okay, yeah, nuclear weapon means what? Okay, a bomb as a bomb. Okay, the bomb is kill you and also kill me. Okay, yeah, I will make sure that I won't have this problem. But if you're curious, I can discuss with you about the solution. Okay? So how to give a writer a relatively higher priority. When a writer appears in the system, all later readers will block. Very tricky. Not very hard, okay? I mean, at that time when I post up this question in the lecture, already several students know how to do it, and they guess I will put this into a midterm so they memorize it. Yeah, then they get a very high score in midterm. Okay, so this is the end of this part. This part is the hardest in the sense that this is the first time that you understand some algorithm that execute concurrently with different processes. This is the first time. Okay, previous lectures on a database, on algorithms, on data structures. Okay, they all give you algorithm for one process, but now we have two processes and how they cooperate. Okay, so that's it, and